December 7th, 1941. Pearl Harbor burns as Japanese Zeros slice through the sky like silver daggers, seemingly unstoppable. For months, Allied pilots whispered in fear about these ghost fighters that could outmaneuver anything they flew. But hidden beneath that sleek fuselage was a fatal flaw, an engine that would ultimately doom Japan's air superiority forever. Our story begins with what seemed like Japan's masterstroke, the Nakajima Sakae 12 radial engine. When engineers first fired up this 14-cylinder powerhouse in the late 1930s, it was genuinely impressive. Producing around 940 horsepower while weighing just 1,200 pounds, the Sakae gave the Zero an incredible power-to-weight ratio that made it the most maneuverable fighter in the world. But here's what we need to understand about the Sakae. It was designed for a specific moment in time, optimized for the early war when dogfighting and maneuverability ruled the skies. The engine's relatively modest displacement and conservative design philosophy reflected Japan's resource constraints and their belief that agility would always triumph over brute force. As we dive deeper into this story, we'll see how this philosophy became the Zero's greatest weakness. While American engineers were already pushing the boundaries with engines like the Pratt & Whitney R2-800 Double Wasp, producing over 2,000 horsepower by 1943, the Sakae remained essentially unchanged. The Japanese had created an engine that was perfect for 1940, but woefully inadequate for 1944. Think of it like bringing a precision rapier to a fight where everyone else started carrying sledgehammers. The Sakae's efficiency and lightweight design had given Japan early air superiority, but as the war progressed and Allied fighters like the F-6F Hellcat and P-51 Mustang entered service with vastly more powerful engines, the Zero found itself outclassed not just in speed and climb rate, but in the fundamental mathematics of aerial combat. The writing was on the wall. Japan had bet everything on an engine philosophy that couldn't evolve fast enough to keep pace with wartime innovation. But the Sakae's limitations were just the beginning of a much deeper problem. While American and British engineers were revolutionizing aviation with turbochargers and advanced supercharging systems, Japanese engine designers were fighting a battle they didn't even know they were losing. The Sakae engine used a single-stage, single-speed supercharger, essentially 1930s technology frozen in time. To understand why this mattered so much, we need to think about what happens when aircraft fight at high altitude. As you climb higher, air becomes thinner and engines lose power dramatically. A naturally aspirated engine might lose 30% of its power at 20,000 feet. This is where supercharging becomes critical. It forces more air into the engine, maintaining power at altitude. American engines like the Allison V1710 and later variants of the Merlin featured sophisticated two-stage supercharging systems, sometimes combined with turbochargers. The P-38 Lightning's twin Allisons with turbochargers could maintain full power up to 25,000 feet and beyond. Meanwhile, the Zero's Sakae was gasping for air, producing barely 600 horsepower at those same altitudes. But Japan's problem wasn't just technical, it was strategic. Developing advanced supercharging required specialized metallurgy, precision manufacturing, and extensive testing. Japan simply didn't have the industrial infrastructure or raw materials to perfect these systems. Every advanced alloy used in a turbocharger was a strategic resource they couldn't spare. The tragic irony is that Japanese engineers understood the importance of high-altitude performance. They tried to compensate with the Zero's exceptional aerodynamics and lightweight, but physics is unforgiving. When American pilots learned to engage Zeros at high altitude and in high-speed dives, they exploited exactly this weakness. By 1943, the altitude advantage had become so decisive that Zero pilots were often forced to fight at medium and low altitudes where their engines could at least compete. But this played directly into the hands of heavily armed and armored American fighters designed for exactly these conditions. Here's a factor that most people never consider when they think about the Zero's decline. Japan was literally running out of the right kind of gasoline. While American aircraft were guzzling 100-octane aviation fuel and later 115-octane for maximum performance, Japanese engines were forced to run on fuel that was often closer to 87-octane, sometimes even lower. Octane rating isn't just a number. It's the difference between an engine running at peak performance and one that's constantly fighting detonation and knock. Higher octane fuel allows engines to run higher compression ratios and more aggressive timing, which translates directly to more power. The difference between 87 octane and 100 octane fuel could mean 200 to 300 horsepower in a high-performance engine. But Japan's fuel crisis went deeper than just octane ratings. Their refining technology was years behind the Allies, and they lacked access to the tetraethyl lead additives that boosted octane ratings. Even worse, as the war progressed and shipping lanes were cut off, Japanese pilots sometimes flew on fuel that was contaminated or improperly refined. We can see the impact of this fuel crisis in combat reports from 1944 onwards. American pilots noted that Zeros seemed slower and less responsive than earlier in the war. What they were witnessing wasn't just pilot inexperience, it was engines literally unable to produce their designed power output due to inferior fuel. The psychological impact on Japanese pilots was devastating. Imagine climbing into your fighter knowing that your engine is producing maybe 70% of its design power, while your opponent's engine is running at 110% thanks to high-octane fuel and perfect maintenance. The Sakae engine, already underpowered by late war standards, was being further handicapped by fuel that wouldn't have been acceptable for a civilian automobile. As the Pacific War dragged on, the quality of Zero engines began to deteriorate in ways that would have been unthinkable in 1941. What we're about to explore reveals how wartime pressure, resource shortages, and strategic bombing campaigns created a cascade of manufacturing failures that doomed even the most skillfully designed engines. Early Sakae engines were masterpieces of precision engineering, built in dedicated factories by skilled craftsmen who took pride in their work. But by 1943, everything had changed. Japan's aircraft engine production was scattered across numerous smaller facilities to avoid bombing, often staffed by inexperienced workers, elderly men, women, and even students. The materials crisis was equally devastating. High-grade steel became so scarce that engineers were forced to substitute inferior alloys in critical engine components. Bearings that should have lasted hundreds of hours were failing after dozens. Cylinder heads cracked under stress that earlier engines would have handled easily. Quality control became a luxury that Japan simply couldn't afford. Perhaps most tragically, we can trace the decline through maintenance records. Early war Zeros routinely flew 200 to 300 hours between major overhauls. By 1944, Sakae engines were considered lucky to reach 100 hours before requiring major repairs or replacement. Some engines failed catastrophically after just 20 to 30 hours of operation. American intelligence officers who examined captured late-war Zero engines were shocked by what they found. Rough machining marks where earlier engines had been polished smooth, inconsistent tolerances that would cause vibration and premature wear, components that showed signs of hasty assembly and poor quality control. This manufacturing crisis created a vicious cycle. As engine reliability declined, Japan had to produce even more engines to maintain the same operational tempo. This further strained their manufacturing capacity and resource allocation, leading to even lower quality. By 1945, the Sakae engine had become a shadow of its former self, not because the design was fundamentally flawed, but because Japan could no longer build it properly. The Pacific Theater presented unique challenges that exposed a critical weakness in the Sakae engine's design. Its cooling system simply couldn't handle the brutal combination of tropical heat, high humidity, and extended combat operations. What had worked perfectly in the temperate climate of Japan became a liability in the sweltering jungles and coral atolls where the war was actually fought. Air-cooled radial engines like the Sakae depend entirely on airflow to maintain proper operating temperatures. The engine's 14 cylinders arranged in a circle around the crankshaft need constant cooling airflow to prevent overheating. In the cool, dry air over Japan, this system worked flawlessly. But in the 90-degree heat and 80% humidity of places like Guadalcanal, Rabaul, and the Philippines, Zero engines began cooking themselves to death. Here's where the Zero's lightweight design philosophy became a curse rather than a blessing. To save weight, Japanese engineers had minimized the cooling fins on the cylinders and used the thinnest possible cylinder walls. They'd also eliminated the cowl flaps that American fighters used to regulate cooling airflow. Every pound saved in cooling equipment was a pound that could go toward fuel, ammunition, or structural lightness. The problem became so severe that Japanese pilots had to modify their flying techniques to prevent engine failure. They couldn't maintain full power for extended periods, had to open the throttle gradually to avoid thermal shock, and often had to throttle back during climbs to prevent overheating. In combat, where engine power could mean the difference between life and death, these limitations were often fatal. American pilots quickly learned to exploit this weakness. By forcing extended high-power combat situations, especially long climbing fights in tropical heat, they could literally cause Zero engines to overheat and fail without firing a shot. It was a textbook example of how environmental factors could negate even the most sophisticated engineering. Ironically, the Zero's greatest strength became its greatest weakness. The aircraft's incredibly light airframe, achieved through meticulous weight-saving measures and minimal armor, had been designed around the specific power and weight characteristics of the Sakae engine. This created a design trap that would prove impossible to escape as the war progressed. When Mitsubishi engineers initially designed the Zero, they faced a seemingly impossible challenge: create a long-range fighter that could outmaneuver anything in the sky while operating from aircraft carriers with limited deck space. Their solution was brilliant: strip away every unnecessary pound and build the entire aircraft around the lightweight Sakae engine. But engineering is all about compromises, and the Zero's compromises came back to haunt it when Japan needed to upgrade its engines. The airframe was so precisely calibrated to the Sakae's weight and power characteristics that installing a more powerful engine would have required a complete redesign. The delicate wing structure couldn't handle the torque of a more powerful engine. The landing gear wasn't strong enough for a heavier aircraft. The entire weight and balance envelope would have been destroyed. We can see this trap in Japan's desperate attempts to upgrade the Zero throughout the war. The A6M3 tried to increase power by using a different propeller and engine variant, but performance actually decreased due to weight increases. The A6M5 incorporated minor improvements, but remained fundamentally limited by the original design constraints. Meanwhile, American aircraft like the F-6F Hellcat were designed from the ground up around powerful engines like the R2800, with robust airframes that could accommodate even more powerful engines as they became available. The Hellcat actually got faster and more capable as the war progressed, while the Zero remained trapped by its original design philosophy. The final nail in the Zero's coffin wasn't just technical, it was strategic. Japan's inability to scale up production of improved engines while maintaining quality represents one of the most critical industrial failures of World War II. While American factories were churning out tens of thousands of increasingly powerful engines, Japan was struggling to produce enough Sakae engines to keep their existing fighters in the air. By 1943, American aircraft engine production had reached truly staggering levels. Pratt & Whitney alone was producing over 50,000 engines per year, each one more powerful and reliable than the last. Ford's Willow Run plant was manufacturing complete R2800 engines on an assembly line basis, achieving quality and consistency that Japanese manufacturers could only envy. Meanwhile, Japan was caught in a production death spiral. As bombing campaigns intensified, engine production facilities were dispersed to smaller, less efficient factories. Quality control became impossible to maintain across dozens of scattered production sites. The skilled workforce that had created the early Sakae engines was depleted by military service and bombing casualties. The strategic miscalculation went deeper than just production numbers. Japan had invested heavily in perfecting the Sakae engine for a specific type of warfare, the quick, decisive campaigns that had characterized their early Pacific victories. They never developed the industrial infrastructure needed for a prolonged war of attrition against opponents with vastly superior production capacity. Perhaps most tragically, Japanese engineers had actually developed more powerful engine designs by 1943. Including the Nakajima that could produce over 1,800 horsepower. But these engines required precision manufacturing techniques and high-quality materials that Japan could no longer provide consistently. Advanced designs sat on drawing boards while factories struggled to produce enough basic Sakae engines to meet immediate needs. The Zero's engine failure was ultimately a reflection of Japan's broader strategic failure. The inability to sustain technological innovation while fighting a global war against opponents with superior industrial capacity. The Zero's downfall wasn't just about one engine, it was about 8 interconnected failures that turned Japan's early air superiority into a death spiral. Underpowered engines, poor fuel, manufacturing collapse, cooling problems, design limitations, innovation gaps, and strategic miscalculations combined to ground the once mighty Zero. The aircraft that ruled the Pacific didn't just lose to superior tactics, it lost to the inevitable march of technology and industrial might.